Hey everyone. So for lesson 9, we're going to talk about hypothesis testing for difference in proportions. And so the example that I found is from 3 years ago. So I'm just going to preface this by saying I know absolutely nothing about sports in general, and I have no idea if this is relevant anymore, and I barely know even what it's talking about. And this is exactly why statisticians should always have domain experts that they're working with. Whenever you do an analysis as a statistician, you always work with someone who's an expert in the area that the data is coming from. But we can still talk about this article and analyze it in the context of this lesson. So it's called LeBron James, Late Game Proficiency Not as Simple as Mere Numbers. So this is February 2017, and the spring before then, ESPN senior writer Mark Stein had presented evidence that LeBron James had difficulties, quote, when attempting a tying or go-ahead shot in the final 5 seconds of the fourth quarter or overtime. So at the end of the game, there was this ESPN senior writer presented some type of evidence saying that he didn't think that LeBron James, his proportions of successes was as high as other people. And so this is a research question. We can literally start here with, okay, we have a research question, and the question is LeBron's proportion, is the proportion of these shots that he makes smaller than the average for the other players in similar situations? And so we can go through our steps. So the first step that we have is to check assumptions and to write hypotheses. So the first assumption that we want to check is the assumption for the normal approximation. So we can see, can we use the normal approximation? And that is to check that the number of successes and the number of failures in both groups. So now in this section, we're talking about two different proportions. And we want to know that in both groups, the number of successes and failures is at least 10. And so they tell us that LeBron was 5 of 47, meaning he was successful in 5 of the 47 situations. And the average among those shooting a high volume of similar shots was 22.7%. So we'll assume there are a lot of players in that second. So there's two groups. There's the group with just LeBron, and then there's the group with all these other players. And we'll assume that group, that's a very large number of successes and failures. So it's definitely larger than 10, even though it doesn't tell us here. They know how many it is, and we can assume that it's larger than 10. But for LeBron, 5 successes out of 47, 5 is not bigger than 10. So we do not have the correct assumptions in order to be able to use the normal approximation if we did have this data and wanted to do our own analysis. Okay, so we checked our assumptions and they don't work. So, we're not going to do the normal approximation, but we learned there are other things we can do instead. And in the hypotheses here, the subscript here, I wrote LeBron and other instead of 1 and 2, but 1 and 2 would be fine also. So the null hypothesis is that the difference between these two proportions is 0, so there's no difference. And the alternative is that LeBron's proportion is smaller than the proportion for other players. So the proportion for LeBron minus the proportion for other is less than 0. That's the alternative hypothesis. The alternative hypothesis is always the thing that we're interested in proving. We're interested in showing that that is true. Okay, and so we can make the assumption that they use something other than the normal approximation since we checked and the assumptions didn't work. So they could use something like Fisher's exact method or bootstrapping. But whichever method they use, they talk about they conducted a one-tailed test for the difference in two proportions. And their goal was to determine whether LeBron is significantly worse than his cohort's average, so than all the other players' average. And they say, okay, we did this. We found this to be true at the 0.025 significance level. So they calculated a test statistic, and then they found the p-value. And then they make the statement that if LeBron's true level of clutchness were equal to the average, then the likelihood of observing 5 or fewer makes, so he only had 5 successes, so the probability of observing having 5 or less, given that these two proportions were equal. So given that LeBron had the same as all the other players, the probability of him actually getting only 5 out of 47 shots is approximately, or less, 5 or less, right? Because you're always looking the more extreme. This is a one-sided test, so I guess maybe since I'm backwards, this will be wrong. But you have your distribution, and you're looking at the tail in the left side because you want to know less than. So you look at the tail on the left side, and you look at what proportion is in that tail, less than the sample statistic, which is 5 out of 47. 5 divided by 47, whatever proportion that is. And so they calculated that that was equal to 0.021, or in other words, you can call that 2.1%. And that's the p-value. 0.021 is the p-value. So that's that area under the curve to the left tells you your p-value. However, they don't tell us the test statistic here, just because it's not that important for the reader to see the test statistic, but they definitely computed a test statistic in their analysis. So then the decision needs to be made of, do we reject the null hypothesis or do we not reject the null hypothesis? And since our p-value is 0.021 and they claimed that they were using a significance level of 0.025, so their confidence level is 97.5, that means 97.5%. That means, so since this p-value is smaller than the significance level, they're going to reject the null hypothesis that these proportions are the same and state the real world conclusion: LeBron is significantly worse than his cohort's average. And that's all. All right, I hope everyone has a nice week.